So last time we discussed toric manifolds. It's also an applied science because with the toric manifolds you have a great collection of manifolds that are completely under your control. It means that toric manifolds are tame manifolds, okay, not wild manifolds. Now let me tell you another piece of applied science, namely equivariant cohomology and various applications. So you may ask why you should think about equivariant cohomology. So equivariant cohomology can be used first in computation of cohomology rings of manifolds. Here I need to comment on the thing that is called the main theorem of algebra. Main theorem of algebra should be considered together with the Galois theory in the following sense. In old days, people tried to find out explicit solutions to algebraic equations. And in some sense, they failed, and they proved that they failed. Okay? So it could mean that it is the end of algebraic geometry. How can you study something that you cannot solve? However, it turns out that sometimes you can say something about things that only exist and that you are not able to find. So main theorem of algebra is the first example of this stuff. You know the number of solutions of equations without knowing solutions themselves. Okay? So it was a good lesson, but people all the time, all over the world, in different epochs of science, forget this lesson. That sometimes it's possible to study the properties of the objects that only exist. So you can compute something without knowing themselves. So like solutions to the algebraic equation. Old idea, count them, find them and count them. New ideas, count them without finding them. Okay? So this thing as a number of solutions nowadays could be modified into something like computation of cohomology. So simple thing is the dimension of the space of cohomology. And we know many techniques how to get this. However, there is additional structure. And this additional structure is a ring structure. In most cases, you can multiply cohomology, and even, sorry to say that, Frobenius structure. So you can multiply cohomology, and then sometimes there is a fundamental cycle to integrate against. And then the issue is it possible to find these structures without knowing cohomology themselves? You see, it's easy to say that now we count. Yes, it is not that easy to say that now we not only count but also multiply. You see, you may think that in order to multiply something, you need to have more control on this than when you count something, right? However, it turns out that using some kind of technique, you can you can compute something about things that you cannot construct. And that's what happened in so-called issue of cohomology ring of some class of manifolds. That's what on my board. And also, this is most remarkable, in so-called quantum field theory problems. It turns out that you can compute something without knowing it explicitly. It was so in two-dimensional quantum field theory, where in most cases you think that you know what you are doing. Sorry, cross it. You know exactly the object. But in four-dimensional theory, because in four-dimensional theory, people in 70s spent a lot of time on studying so-called instantons and monopoles and other stuff. And I can recommend the great talk of, I think maybe it was Stauss or Donaldson. So there is a great series. I want to advertise the great series of talks arranged by Professor Yao. It's so-called Harvard. I thought it was so-called Harvard talks on mathematics, where old masters explain their point of view on some great events in 80s. They are on the internet. Okay? So you can read it there. Okay. So still, so there was some activity. People found some instantonic solutions. People started to find moduli spaces of these solutions. But it turns out that it's possible to compute a lot about them. And I think that the leading result is the result of Nikita Nekrasov and collaborators on instantonic counting in super young mills. Okay? And it's exactly the place where equivariant stuff showed its power. By the way, it was awarded by the Fields Medal that went to Okunkov for Nekrasov-Okunkov theorem. So it was conjecture made by Nekrasov and proof given by Nekrasov and Okunkov together. Okay? And because of this, I feel my obligation to lead you there to some extent. You see, not I am not going to explain hundreds of pages and a lot of combinatorics. I'll try to give you the way, to open you to the door in this world. Okay? So first is the computations of cohomology rings of manifolds. Second, that's also interesting. It's computation of equivariant volumes of holomorphic maps. From CP1 to toric manifold. Maybe sometimes you can even replace even manifold with general C star action. So there are two versions. Why this thing is interesting? This thing is interesting not only because you can compute nice formulas, but because studying these equivariant volumes, and of course not only one particular equivariant volume, equivariant volumes as a function of degree, and summing them, you get so-called J function of given type. So this function is so remarkable that you can construct out of this J function, you can construct so-called mirror map or special coordinates. And special coordinates, okay, I'm sorry. When I say mirror map, it is a standard terminology. It's very bad terminology because it's not, so this mirror map is a special parameterization, special coordinates. I'm sorry, it's called mirror map. Special coordinates in the mirror corresponding. So special coordinates, they are inside this J function. It is not widely known, I mean, all this. And I even don't want to stop here because then you can compute the third thing. Compute equivariant volume of instantons. In four-dimensional supersymmetric n equals 2 theory. And here I'll have Nekrasov function, and I don't know how people used to call this function. I'll call it n. Okay? It's called Nekrasov function. And even with all these achievements of Nekrasov theory, I would like to say that there is an open problem. You see, the science is dead if it doesn't have an open problem. We know, we learn something, we study something because it opens new questions. And the question is, of course, okay, we have Nekrasov function, like J function. So J function is related to WDVV. And here is the old question of four-dimensional WDVV. It's a question. So if you follow these considerations, you would be able to understand this question. So here the key thing is this J function of given type. The equivariant volumes of space of holomorphic maps. Now, in this setup, in this setting, I want to mention something. When we say that we compute equivariant volumes of holomorphic maps, here we have these holomorphic maps under our hands. We can touch them. Mostly we can touch them. There is some subtlety when you cannot touch them. It's when you have holomorphic maps into not toric manifold, I need to say, but in Complete. Complete what? Intersection. Submanifolds. Okay? So not only toric manifolds are governed by this, but also complete intersections of manifolds. And let me tell you why. It is because so-called complete intersections of manifolds are actually not manifolds, but supermanifolds. So it means that you have an even direction, that is this toric manifold that you have. But you also have an odd direction where equations are. And that's why you have supermanifold with the action of the, say, C star. And it is very similar to the manifold with the action of C star. And you can use the same technique. However, what is important here? Important here is this complete intersection. Because if you have these equations and you impose them, and you consider only one component out of them, it would still be a manifold, submanifold. But it would not behave that nice. And here, these complete intersection submanifolds are analogs of the set of all roots of algebraic equation. Treatment of complete intersections allows you to find nice formulas. But if you restrict yourself to a component, it could become a wild problem. By the way, you know that you can embed all algebraic manifolds into CPN, okay? Why it's not that easy to compute everything about them? It's because when you embed them, you locally describe them as a set of solutions to algebraic equations. Locally. It means you do not have a global picture, only local. And that's why it's a hard problem. Like you see, if you ask, I'm trying to find the root, I'm studying the root that is close here and there, it's hard. If you want to say all roots, it's easy. That's why here complete intersection is very important term. You see, just to give you a feeling why it's important. Now, here, in the four-dimensional story, what we see is the avatar of the old French game of two resolutions. So paradigma of the French school of 50s is, I mean practical paradigma, is that you can have several ways to compute the same thing. So French school mostly computed cohomology using different resolvents. And they spent a lot of time showing that you can have one resolvent, another resolvent, and answer is the same, and what is the condition for resolvents when the answer was the same. So here, in four-dimensional theory, we surprisingly have the avatar of the same idea. There are two ways to describe the moduli space R. So consider what I'm saying right now is an advertisement of four-dimensional Young-Mills theory for mathematicians and mathematical physicists, okay? Because it's a case where you have two different descriptions of modular space of instances. And it's good, because using each of the description, you can use your own tools. And then you can compare and get something like a Fields medal. Not that bad. So description A, it's a so-called quantum field theory description. I'll call it Donaldson, Witten. The modular space is the space of connections with the condition that there are self-dual, and you take a factor over the gauge group. So it is, of course, a quotient. And of course, so this is a quotient. However, this quotient, actually you can consider this quotient in three ways. Okay? I will throw away one way and I'll describe two ways. Okay? So this thing is the same as connection that are complex connections. And they are integrable. And we divide with the complex gauge group. And here you need to impose stability. So here this is the space of holomorphic bundles, together with some stability condition. Honestly, let me be honest. Sometimes these are bundles, sometimes they are sheaves, okay? And here we divide over the complex gauge group. And here what we have is actually a Hamiltonian reduction of the submanifold. To see here that it is a Hamiltonian reduction of the submanifold, and we studied Hamiltonian reductions last time, I need to say, what is this submanifold and what is the Hamiltonian reduction, right? Of course, you assume that it will be Hamiltonian reduction due to this gauge group. But I want to be a bit more explicit. So if I have a connection, I can construct F 0, 2 curvature, and I can construct F11 curvature. And also there is F20 curvature. That is clearly complex conjugate to F02. I'm sorry. I would like to consider everything on the moduli space of instantons on the complex. Sorry. Manifold. You see, you may assume that it's a complex manifold by knowing me. You know that with all my respect to smooth science, I am hiddenly complex analytic or even algebraic geometer. Okay, so of course I mean this. So so this is complex conjugated to this. It means that I have a curvature and I decompose it in forms. So what is a submanifold? This submanifold is given by the condition F02 equals to 0. So it is a set of algebraic equations. Locally, it is this. And as we discussed last time, that A bar should be considered as a holomorphic coordinate on the space of connections. We discussed that. So this is a submanifold. And now you see, complex manifold, complex scalar manifold. And now it turns out that this guy is what? Is a moment map for gauge transformation. Let me recall that I consider the symplectic structure omega trace delta A, delta A. So the symplectic structure. And this symplectic structure is very familiar to people who study two-dimensional Young-Mills theory. In two dimensions, everything is the same, you just have no omega. So it is very trivial generalization. Pasha, is it clear what is written?
It's a bit dark then, and it's not that visible.
Ah, okay. So it is dark here.
Yes.
I'll improve the light. Okay, I promise. I'll call it omega. Is it visible now?
Yes.
So it is this symplectic form. So here is symplectic form. There is the gauge transformation. And similarly, very similarly to two dimension, you may compute that this is a moment map in this symplectic structure. But let me make an observation that 0 of this moment map is exactly the piece of self-duality condition.
But actually, I didn't understand. So you first restrict to the submanifold F02 equals 0, and then you restrict to the 0 locus of your moment map.
Yes, exactly.
Okay.
So you understand. You said, I don't understand, and you explained exactly what.
Okay, okay.
Yes.
So in two dimension, all connections are integrable.
Yes, yes, absolutely. That's why we like 2 dimensions. I mean real 2 dimensions. So Sam, you are from differential geometry side, I know. Because would you be algebraic, you will say in one complex dimension. Okay, yes. Yes, exactly. So that's what one has to know about instantons. So there are 2 descriptions. First, it's Hamiltonian reduction. Second, it's a factor with respect to the complex gauge group. And we will use both of this picture. However, there is a third one that is not used. And it is not used yet, and it's kind of a pity. It's not completely used. And the third description, and I know that it was the starting point for Nekrasov and Shatashvili these days, is that this moduli space is also a hyperkähler reduction. So I'm sorry. I need to say that this fact is partially used by Edward Witten in his work on relation between gauge theory and Donaldson, between gauge theory and Langlands. You see, it's a pity that this space has another structure that is not used in the construction. So let me briefly say what hyperkähler reduction is. Okay? And I will not go into detail because I will not use it. But I cannot just ignore this fact, right? Actually, if you study instantons not on the complex manifold, but on the hyperkähler manifold, you will have the following fact, that this M would be a hyperkähler manifold that is obtained by the hyperkähler reduction. And okay, I'll say it in words because I will not use it. But I cannot just ignore it, okay? It would be non-fair. In the hyperkähler reduction, you have not only one moment map, but 3 moment maps. You have 3 moment maps. You have 3 3-dimensional space of 3-dimensional space of symplectic structures. Okay? And what you do, you impose 0 of 3 moment maps. all together and divide with respect to the gauge group. On the hyperkähler manifold, like case 3, or non-compact, three moment maps are omega Kähler, omega to 0, omega 0 to F. So these are three moment maps. You put all of them to 0. You divide by the gauge group, and in the hyperkähler theory, you have the group of rotations. And this group of rotations rotates you three-dimensional space of symplectic forms into each other. And similarly, it rotates you the moment maps. And in this way, all components of self-duality equation become an orbit of this hyperkähler group. So we know this, and this nice fact was a motivation for Nekrasov to study this issue, and they wanted to study hyperkähler reduction formulas. But it is not properly used. It turned out that this point of view, the third point of view, was not needed. Okay? So maybe someone could get more formulas and more properties using this phenomena, especially because in Nekrasov theory, the manifold X4 is the C squared. That is, of course, hyperkähler manifold. Okay. But all these descriptions are quantum field theory descriptions. And I started to tell you that there are two resolvents. Okay? If you would like to compute something here, you just have to write down functional integrals. But there is a second approach. And the second approach, you see, two different, I'll keep this. And second approach, approach B, is ADHM like description. That is finite dimension in nature. I call it ADHM-like because the original ADHM construction was the construction of instantons on S4. It is because at that moment, physicists were interested only in instantons on S4. Later on, people, this mathematical physicists, start to be interested in instantons not only on S4, but mostly on complex manifolds. So while there is no general description, but I 99% am sure, I am 99% sure that there is a description on toric manifold. So original description is a description on C square. That is a particular case of the toric manifold. So the idea of HDHM description is the following.
So, Andrei, so a silly question. So the old ADHM was about ordinary angle. There was nothing super about it.
It's about, you see, good point. When I'm writing down equations, okay, I am studying so-called bosonic piece of something.
Yeah.
So it's like when I'm writing down algebraic equations in algebraic geometry. However, when I'm treating them in algebraic geometry, it's very useful to study differential forms. And the same happens in theory of connection. So so when we will study differential forms on the space of connections, you will see these so-called fermions.
Right.
And it was also discovery of Edward Witten, who started studying that. So differential forms on the, so whenever you use the language of differential forms to treat some problem in geometry, it means that you mostly go to supersymmetric theory.
So you're saying that the modular space you're talking about now, it is also there's nothing super about it. The super thing is to sort of facilitate localization on instantons.
I would say that it's not the modular space that we would like to study. It is the cohomology ring. And of course, this cohomology ring would be a ring with respect to, now you ask, which differential? Now there are many choices. In the traditional Edward Witten approach, the differential was the Theorem differential. Nowadays, I mean last 10 years, people also study Dalbor differentials of the modular space. Here I need to say that the twisting of n equals 1 super Yang-Mills that leads to Dalbor differential on the modular space was constructed by me and E.O. Hansen in 94 or 95. But Edward Witten shouted on me, telling me that I'm stupid. And I was so frightened that I canceled my participation. And there is a paper of the brave E.O. Hansen, who says that he doesn't care about Edward Witten. And the paper is right, and he published it. And there is a paper of Andrei Hansen that is a pioneering paper on the Dalbor on the modular space of instantons from n equals 1. I am a coward participant. Okay, I I was preparing for the battle, but I ran away from the battle. So so I say that, look how great Jaganson is. Unfortunately, he quitted science. So then he worked with Wafa, but then he quitted science. Okay, so I was a coward, you see, what to say. But at least I can mention it. Okay. So I was there.
So, Andrei, you asked me to be the time policeman. So now,
Yes.
so it's
Yes.
45 minutes.
Okay, so I'll.
Mhm.
I do not want to hurry up, Pasha. Shouldn't
No.
I hurry up?
No.
Is the speed proper? Because
Very
now,
good.
when I am tired about this removal, people say it's removal. So from place to place, moving. So I think that I'm thinking slowly and speaking slowly. So I need some external observer.
No, it is visible that you are very tired, but the speed of the lecture is I don't know, it's good for me.
Okay, so it is visible that I'm tired.
It is visible that you are tired.
It's good that I am not a woman. Okay. A woman would be disappointed. I am not. I'm just very tired. Okay. So now that's why now it's a break. I'll continue and we'll go into a covariant world. Okay.
Right.
So 5 minutes break. Pasha, how much time had passed?
Well, I guess 5 minutes. That was
5 minutes.
5 minutes.
Okay, good.
So yeah, Andrei, I guess you could have like a light on the right side of the board. It's yeah, that side is a bit darker.
I know. You see, I will change the light. I will change the light settings. So I'm in the new room, and I'll change the light conditions because I also need to avoid blicks. If I turn more lights, there'll be light spots.
Yeah.
So I need so I need to do it, and I will do it. Next time, I promise you, light would be okay.
Yeah. So ADHM is kind of.
Well, now let us continue.
So it's a quiver variety, right? So it's some sort of a quiver variety. So it has some combinatorial structure to it. So there should be some other quiver for complex four manifolds.
How to say? Formally, you are right. But let me explain the essence of ADHM. Okay? Because everything has its soul and its body, and even mathematical construction has a soul and body. So ADHM construction has a deep idea inside it. Okay? So let me explain you this idea, and then when it will come, then when we will come to ADHM, you will see how this is realized. Okay? But first, there is idea. Idea of ADHM construction is the following. So very general idea. Philosophical idea. So I will not prove it, I'll illustrate it, okay? All natural vector bundles are bundles of cohomology. So let me illustrate it as in an example. That is not ADHM, just for you to feel this idea. Suppose you have Cn, okay? And suppose you have surface given by equation f equals to 0, or many equations. How do we understand the tangent bundle? We take vectors from Cn. You see, in Cn, you may identify tangent vector to the full Cn and impose condition. Okay? And this condition actually means that vector is tangent to the hypersurface. Okay? So if f was 0 here, then it would be 0 if we shift by the vector v. And note that this is not a differential, it's an algebraic condition on v. So it's not a condition on the vector field, it's condition on the vector at a point. And if you have a set of equations, you write it this way. So what do you see here? Here you have just a two-set complex, okay? So you have Cn, and you have differential that is contraction with dfa. And here we have Ck. And the tangent bundle is nothing but the cohomology. You may also consider not the submanifold, but you can also divide by subgroup. So if you divide by some group that has a Lie algebra, then you have the Lie algebra acting here. So I call this rep, means representation. Now, this Lie algebra preserves the manifold if combination is 0, right? Because if you do this and this, you will get the action of the Lie algebra on the set of equations. So basically what you see here is a complex. So then the tangent band bundle is the bundle of cohomology of the complex. And according to some philosophy, all manifolds are quotients of submanifolds, of intersections of hypersurfaces. So when people say bundle, it often comes from cohomology. So there was some construction. By the way, if you keep this in mind, you may say that, Pasha, that from this construction, sometimes you can get not bundles, but sheaves. Because the rank could jump. You can start having cohomologies here or here. And you may think that you should think, why should? You may think that it's okay. That what we call natural bundles could have such phenomena. So what I actually described was kind of a tangent sheaf, okay, as cohomology of this complex. Okay. So the same thing happened if you are trying to study the bundles or maybe sheaves of some type on the manifold. You start with the linear operator. Acting on some space. W, okay? It could be the general linear operator, but it's not the most natural thing that you would like to get. Maybe you would like to impose some conditions on this linear operator. So actually it's a matrix, okay? And you want it to have 0 somewhere, okay? Now, if we are talking or thinking about cohomology, it would be better to have a differential. So this is, so what is this? Equation on the space of linear operators of some kind. So you say quiver. So when you say quiver, you mean that You don't have all arrows. So when you say quiver, you say something like this. Yes.
Mhm.
So quiver is a subset of all possible arrows. Okay.
Mhm.
So that's what I call the differential of the special type. You may say quiver. So when I said you have zeros somewhere, it's basically the same. Not all arrows are allowed. Then you have the great thing. You have these equations, and of course you have the moduli space of this equation. Because there is a natural symmetry. And such symmetry preserves this equation. And of course, what you would like to study is these equations, moduli these relations. I'll call it mod with a tilde. So what you definitely would have would be the bundle of cohomology of D over the mod tilde, right? Now, sometimes this mod tilde, sometimes is a product. X times some mod. And then this is the, and sometimes this mod is exactly the universal moduli space of bundles on X. So this is universal ADHM construction. So such construction exists in many cases. However, sometimes it gives a complete set of bundles on X. Sometimes it gives you the moduli space of bundles on X. Sometimes it's a subspace. So when you have this construction, the only thing that you need to check is if you actually have the complete set, the complete moduli space. So it's the only thing that you need to prove. But if you have it, you are done. Because you have complete control of everything. You have quadratic equations, just set of quadrics. And you have a symmetry. And in many cases, you have extra symmetries here. External symmetry.
Sorry, I'm completely lost. What is D? Can you explain how the usual ADHM for either S4 or C squared works here?
I'm sorry that I made you completely lost. So usual ADHM
Mhm.
in the usual ADHM you have kind of complicated space W that contains of so W, as far as I remember, is something here and something here. And this something is also divided into two spaces.
So I guess the point well, I'm
You
really
will
don't
write a
understand.
quiver.
So the
You
point
can
where I
write
don't understand, Andrei, so you started explaining that when you have a quotient of a submanifold, you can describe its tangent by cohomology. That's fine, but when we are talking about instantons, then it's you're taking a submanifold in something infinite dimensional and taking a quotient by an infinite dimensional group. So how do we pass from that to a finite dimensional description?
I am not passing. It's a it happens. So you see. So, but you asked me two questions, and I haven't answered the first question. So our answer of the first question is that you have not a general operator. You see, you have you have big space, finite dimensional, and you have operator. Okay, you call it quiver, that you have maps here, some particular maps, and you are writing these equations.
But if say we want to derive ADHM from the philosophy that you are saying, then we are starting from some infinite dimensional picture.
No, I cannot derive it.
Okay.
I cannot derive it. So what I'm saying right now is that for me, ADHM is just this general construction that, and you improved my presentation when I said linear operators of the special type. I said somewhere it has zeros. You said better. You said that you have a quiver. So you have some kind of a quiver. And you have a linear operator. So whenever you have errors, you put a linear operator. Whenever you have no errors, you put zero. In this way, you have a linear operator from the total vector space to itself. It has non-trivial and non-trivial something only where you have errors. Okay. So you can, in this way, you can write it for any quiver. So you write a quiver. I don't know, something. So for any error, you write a linear operator from the vector space associated to the node to itself. Pasha?
Yes.
So and you call this thing D.
Yeah, right. But I mean, this is ultimately still, it's an ansatz for some answer, which is a beautiful answer, but it doesn't explain how does it come about.
Of course. So what I mean by ADHM is the following: you study quiver theories. So it's simple. If you have a quiver, you have operator D. That is the sum of operators. Not that is a. Yes, it's a direct sum of operators associated to errors. And then you impose condition d square equals to 0. And there are natural symmetries, of course, the symmetry U associated to each node. of the quiver. Okay.
So okay, so come again in this quiver. So what is D? So we are considering a bunch of vector spaces at nodes and operators between them.
Exactly. We consider the bunch of vector spaces of nodes.
Ah, so D is the data of the linear maps. Mm-hmm.
With number of nodes. So we consider W, that is V1 plus V, the number of nodes. So we consider very general operator D. It acts from W to W, but D is non-zero only if there is an arrow.
Yes.
And you also have a group G, that is G1 times G number of nodes. And you are writing D squared equals to 0. So it's a main equation. So there is a thesis of Cartan who said, I wonder how many equations have this form, D squared equal to 0. You impose this equation. And of course, this equation has a symmetry. And you divide this equation by the symmetry by G. So when I say G, I mean U, I mean D goes to G, dG, G minus 1 dG. So this is a universal construction. As an input, it has a quiver, okay? As an output, it has this space. There is a moduli space here.
So on some kind of psychological level, this reminds of the moduli space of flat connections, which is defined on the level of infinite dimensional reduction, but can be given a purely finite dimensional description as sort of group homes from pi 1.
Yes.
Right.
But here I want to say that I would like to consider this as a purely linear algebra construction. So what is important is that whenever you have this thing, you have the space mod tilde and the bundle HD. Actually, not a bundle, as I mentioned, but a sheaf. This sheaf, of course, has different chain classes, being a sheaf, right? So this is the construction. You see, this construction knows nothing about say instantons in some space. It's just the construction per se. There is such construction.
So in this quotient, what is the total space of the bundle? What is the mod twiddle?
Mod twiddle is the moduli space of solutions to this equation.
Okay, and what is the total space?
And it's a vector bundle. It's not a principal bundle.
What is the fiber?
Cohomology of D.
I see. Okay. Yes.
So it is a hint.
Okay.
So when you have an equation asking some linear operator to be a differential, it automatically comes together with cohomology.
Yes.
So in this case, you automatically have this construction, canonically, HP over mod twiddle. So this is how people say, this is an animal. This is a kind of universal mathematical construction. But what happens is that this universal mathematical construction may be applied in many cases. Okay? And one of the cases is that sometimes the space M twiddle sometimes if you are lucky in choosing a quiver. So now it comes to the art of constructing a quiver. You see, this construction exists for all quivers, but sometimes if you know how to choose a good quiver, this mod tilde would give you mod times x, where x has some dimension, of course. If you are lucky if you know how to construct good quivers, you will get this. Moreover, if you not only know how to get this decomposition, but you also know how to make this mod to be universal modular space of rank R and some Chern class bundles, it's exactly what you need. It's a holomorphic bundle. Equipped, so you already have a holomorphic bundle. So what do you need? And then, if you are lucky, you can use the construction of Donaldson in the dimension equals the dimension of x. So 4 is not special here. The c square is not special here. If you know how to play with quivers, you could probably construct it in many cases. And here, since everything is complex, yes, holomorphic complex, linear operators, quadrics, they're holomorphic equations. You have this universal bundle that you are looking for. And moreover, when you have this quiver, sometimes you can also add external symmetries. And you can consider the stuff equivalently with respect to these external symmetries. You see, I'm trying to separate the piece where you need to make creative decisions and piece where we have standard technology. Okay? So if you are lucky, so what is ADHM? For instantaneous. If you are great, like Atya, Drinfield, Hitchin, and Manning, you know what is the proper quiver.
Mhm.
And after you guess this proper quiver or get this proper quiver, say for C square, you might try to generalize this construction to toric manifold. And one man promised me that he knows how to do it, and another person told me that he knows how to do it, and that's why I'm only 99% sure. And I have a feeling that it is doable, and for some other reasons it should be doable. That's why I am 99% sure that it is doable.
Mhm.
So if this is doable, then you have another description of the Chen classes and again equivariant cohomology on this space. Finite dimensional description and infinite dimensional description. Not related to each other. It is kind of important. So let me tell you the truth. If you start apply ADHM construction, sometimes you will get structures that are not bundles at all. Sometimes you will get construction that are just sheaves. So to be a bundle, it's an extra condition. To be a bundle means that this sheaf is locally free. Why should it be locally free? However, sometimes it is locally free. You know, it's like when you describe a manifold by the set of equations. You may impose conditions that the manifold is smooth. However, from the point of view of algebraic geometry, when you impose a set of conditions, there is no reason for the result to be smooth. So it's like 50-50 game, 50% game. Sometimes it is smooth, sometimes it's not smooth. So that's why algebraic geometry treats them on the equal side.
Is this the case that so this vector space are the space of holomorphic sections? So you can glue them together to be a global holomorphic section.
So this vector, it's a good point, Sam. So how to treat this vector space?
Right.
You may consider it as a fiber, and also you may consider it as a space of global sections. Sometimes, under certain conditions, these two spaces are isomorphic. Sometimes not. So you may think about it as so for my philosophically, I would say that the fact that we have a bundle is similar. You see, I'm using this non-mathematical word similar to the case of regularity or smoothness of the manifold that appears after you impose set of equations. Do not need to be and this place is it's the key point of misunderstanding and quarrel between mathematicians from two different camps: smooth people and algebraic people. Smooth people would insist that it is a bundle, and otherwise they would say that things just do not exist. Look. Consider such manifold. Xy equals to 0. For algebraic people, it's a perfect quadric. For smooth people, not a manifold. So, for smooth people, such thing does not exist. They say, we study only such objects that are smooth. This does not exist. For algebraic people, it's a perfect thing. Moreover, such singular things are in many cases the places where computation are localized. Okay. So when you use localization, you may localize not on the smooth configurations, but on singular configurations. But this is the question of what are we studying? Do we allow this thing or not? Like in smooth business, people like non-analytic functions because they are smooth. Okay? But these non-analytic functions from the smooth camp just do not exist from the algebraic camp. Okay? So actually there are 2 points of view. So poor physicists were completely confused. They thought that they are talking to mathematicians and they expected to get the same result, the same answer from mathematicians. So mathematical physicists were surprised when they got different answers from people from this camp and this camp. Okay? And this came down to physics, I mean to mathematical physics, because there are people who are doing gauge theories and who are doing D-brain, and some construction exists here and do not exist here. You see, when you are doing gauge theories, you assume that you have a bundle, not a sheaf. It's an axiom. You put in your book that you are studying gauge theory, and gauge theory is this and this. So you cannot have anything else. So when you are studying D-brains, you consider gauge theories as something effective. And brain configuration could produce you something more, something like a sheaf. That's why, so this is mathematicians, and this is mathematical physicists. algebraic and D-branes against smooth and gauge theory. And yet, we are not considering people who are doing gravity. Because when you try to do gravity, you will also see somebody who says that gravity is something from the smooth point of view or something from the algebraic point of view. So I'd like to mention here this very important division. However, sometimes, in many cases, there is a space that satisfies both camps. Okay, like everybody likes CP1. Okay, it is good from the smooth point of view. It is good from algebraic point of view. And here, mathematicians and physicists from these two camps agree. Okay, Pasha,
Yes.
do you
Yes.
follow this?
Yes.
Isn't it too abstract or too philosophical?
No, I'm fine with it. No, I'm fine with this. I understand that, I don't know, partition of unity is a very ugly construction.
Well, it depends who you are. It's not a question of ugliness. It's a question of philosophy.
No, I think by training, I'm kind of from differential geometry camp, but I can appreciate that the construction is very ugly. And that's, well,
It's not.
it's,
no,
it's very
no,
artificial. What?
You don't. Sorry, I failed to show you that these two are two different philosophies.
No, I understand.
You should
No, I
not
understand
use.
that there are different ways to glue objects, I guess.
It's a different ways to view geometry.
No, I understand, but this is about different ways to glue objects.
You know, not quite, because people from the algebraic camp would
No,
say
for instance, toric varieties are also glued, but they're just glued in a different way.
so for people from algebraic camp, they don't say that toric varieties are glued. They will say. So I prefer to say the toric variety is start to the end compactified with stuff.
But you can see that there are pieces that look like C star to the end, and they are, yeah. Anyway, they have whatever Zariski open sets that look like familiar pieces.
Yes. But from people from algebraic set, from algebraic point of view. So I know people from two sides. I prefer the smooth view on toric varieties, but people from algebraic set say that toric variety is just a ring or field such and such, described by such and such algebraic data. Okay. Still, okay.
But this also corresponds to, I think it also corresponds to a kind of gluing, just a different kind of gluing, which sort of gradually imposes conditions on your ring of functions by going from a larger ring to decreasing it.
I would say the following. You see, I actually think that while I don't want to talk about philosophy, sometimes when it comes to when you cannot ignore the philosophy, you have to say, look, here is the philosophical description, the distinction. Yes. Here we have just two different definitions.
Yes.
And it's not a question who is more beautiful. One definition or set of definitions against another set of definitions.
Well, from the smooth category, when you take a limit, you have degeneration, and this degenerating object came out naturally. It's not a...
Yeah. You see, actually, it's like man and woman. they make a family, but something that is natural for one is a limit for another. Like in the smooth category, you have singular objects this way. There is also the opposite thing. It's called the theory of hyperfunctions. In the theory of hyperfunctions, as far as I know, people are treating smooth functions as some limits on the generations of algebraic functions. And that's why you see it's like yin and yang. They come together. It's very natural. So we need to see them. Okay. We need to see these two philosophies. It's not the question that one is better than another. Two philosophies, 2 points of view. Okay, it's better to be mathematical physicist. You can accept two different philosophies. In particular, in mathematical physics, it's a question what is fundamental, what is effective. When you say that gauge theories are fundamental, you mean something. Or you may say that string construction is fundamental, or deep brain construction. You mean something else. Okay. I hope that later on we will come back to this issue, and now I want to keep it like this. So,
and you wanted me to be the time policeman, so it's the time policing time.
So it means that still I'd like to say, I want to make a round. When I start something during a talk, I have to finish it during a talk. Right. So there are two ways to construct this mode. One way is smooth and infinite dimensional. Another way is this quiver algebraic. And the fact that they describe the same moduli space is great. It's a great thing that they describe the same moduli space, because you can produce out of it a lot of nice theorems. A lot of nice theorems could be produced by these two, I would say, resolvents of the same space. That's why it's so great. Two resolvents. And it is that sharp in dimension 4. Because in dimension 2, in real dimension 4, because in dimension 2, we mostly can write down the holomorphic maps. However, we also can consider transcendental calculations, and we will do it later on. And it turns out that the key thing, the key point that relates these things are, you may say, equivariant volumes of Giventhal and Nekrasov.
So
J function and N function.
So I'm confused about something. So that's about sort of the partition function of the A model in genus 0, I guess. But in some simple case, I guess there's no equivalent model. It's just counting question. So I guess the moduli space is 0-dimensional. You're just counting points. But I guess you're interested in the case when it's not 0-dimensional, and then you need to count somehow, and then you need the notion of volume, right?
Actually, you are counting points with weights. So actually, when you say counting points, you are kidding yourself. Because on the side, when you are counting points, you actually are counting points in many problems. So there was a set of problems indexed by one integer or several integers where you are counting points. But then you are considering the generating function.
Yes, yes, of course, of course.
And that's why.
But in each term in the series is just an integer counting the number of I don't know, curves passing through some cycles.
Yes. But what is most interesting is that two functions are equal, or one function could be made into another function by some overall transformation, like mirror map or something like this. And this is extremely interesting. So you need to put in parameters. So one of the parameter is a covariant parameter. So it's very important. So one of the discoveries in mathematics was that if you have a manifold with external symmetry, it's very important to study covariant differential, not as a tool, not just as a tool to compute something. It's not a tool, it's a question. Because a covariant parameter is a question, it's a parameter in the problem. And we know that problems in mathematics should be considered in general position. If you want to understand the structure, you should consider the problem in general position. And discovery of a covariant differential is very important because it allowed it to add parameter in the problem and consider it in general position. In particular, let me show you a formula without derivation. Unfortunately, because of the fact that I am tired, you see, I cannot speak with the double speed, double with respect to today's speed, and I cannot discuss it in 3 hours. I can discuss only 2 hours today, but that's why next time we will see that the formula for the Frobenius structure of the ring of cohomology of CPN has an interesting modification. It has a modification like this for quantum cohomology.
So there's nothing equivalent here, right?
Yet. But it also has remember I had sigma I'm sorry, sigma minus we will discuss and derive this formula.
So this A's, those are the equivalent parameters.
Yes. Those A's are equivalent parameters. There are n plus 1 of them. And there is also Q. And this parameter is for the degree. And all these come together.
So N is the same N as in CPN.
Yes.
Okay.
So here you already see the structure. A's, Q, you see?
Yeah.
Something interesting is cooking here.
Yes.
That both equivalent parameters and Q deform something that you thought would never be deformed.
Mm-hmm.
The ring of cohomology of CPN. You see, to deform, you see, let me show you my feeling that to deform a ring of cohomology of CPN
Mm-hmm.
is something like deform a multiplication table of integer numbers. So
Right.
in the first half of 19th century, people thought that there are some structures, that there are some objects that are rigid and undeformable, like electron, you know, like elementary facts of mathematics, the ring of cohomology of CPN. And now we see that it is deformed in two different ways.
Mm-hmm.
And when you deform it in this way or in that way, you see that it becomes a semi-simple ring in general position.
Mm-hmm.
And moreover, you can change Q and you can compensate Q by changing A. Isn't that interesting?
What do you mean? Sorry.
I
What do you
mean that you can by changing A, you can change Q. Viet theorem. These
Yes.
are roots.
Yes. Yeah. Yes. 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 Yes.
By changing roots, you can change
Mhm.
this coefficient.
Yeah.
But while
Mhm.
you think that this coefficient is related to sigma model, to non-trivial mapping, while these A's have nothing to do with the maps, they are pieces of the structure of CPN itself.
Mm-hmm.
But in this answer, you see that they are related. That's why such formulas like this. So not
So
only you deform things, you start to think how it happens that you can trade one for another.
So what you wrote is an instance of this given tiles function.
No. What? It's not an instance. So given tiles function is more complicated, but in some sense, yes.
Mm-hmm. All right.
So it's very good. So it's very important to meditate on given tiles function
Mm-hmm.
and meditate on Nekrasov's function.
Mm-hmm.
Or let me criticize Nikita Nekrasov. I always say good things about my friend, but here I need to criticize him. Okay? He ignored. He did not found all properties of given tiles J function in his N function. And that's why, from my point of view, he missed WDVV4.
Mm-hmm.
So I consider this as a mistake. Not that he not that he made a mistake in theorem. No. The mistake is that he missed a set of theorems. Okay?
Mm-hmm.
And we will study all this
Mm-hmm.
in what follows. Okay?
Sounds
And
great.
and we will not do it on. We can do it on Friday, but Pasha, you as
Sorry.
always are on Friday. So we will do it on Wednesday. And
No,
once
but,
again,
Andrei, it shouldn't be just about my presence, but generally, I think Thursday and Friday are supposed to be different kind of things, right?
yes, you see, I'm so sorry that I missed 2 Wednesdays. You can't even imagine, but you can see what happens to me because of this removal, because of this moving.
Right.
So you see, darkness is not
Yes.
only on my board, it's also on my face, you see.
Oh.
Okay. But I hope that we will discuss everything in the proper speed, and please hold me if I try to run too fast or I.
Oh yeah, there are these buttons in Zoom. Like, where are these buttons? Like, go slower, or like, I went for a cup of coffee, or there's some buttons.
Shut up.
Yes. Forgot where they are.
Yes, 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 yes. As your father gave me an advice that somebody needs to hold me.
Yes. Can't find them. Anyways.
So please ask me questions. I'm really willing to share with you not only my knowledge, but also my feelings about what is going on, that I actually think is important. Okay?
All right. Yeah, thank you.
Okay, so see you next Wednesday. And then I need to ask Dong. Dong.
Yes.
Yes, what are we going to discuss tomorrow?
Yeah, actually, at first I can excuse me because I'm on the public transportation, so I think you hear a lot of noise right now. Okay, so we discussed about.
Maybe you are busy. I don't know. So
I'm not busy. I'm just sitting here in subway. Just excuse me for noises.
No. You see, noise is okay. So what are we going to discuss tomorrow? Because Don, you see, if we skip this, we will ruin the tradition. Okay?
Yeah, I'm afraid that.
And I don't want to ruin the tradition. So in Russia, we used to ruin the tradition of Russian Empire, and still we didn't recover yet. So it's good to create tradition, not to ruin tradition. Maybe so it will be better if we discuss it orally, because if you just write me a letter, so you need to give me a theme, okay?
Oh, and how about this? You mentioned that you're going to discuss about J functions and its equivalent versions on next Wednesday. And I think it would be good if you have some introductory course on the J functions itself. So,
but you see, this is, I want to give it to general audience.
Okay. So you want to give it to the general audience. So
yeah,
let's keep it on the Wednesday. Let's keep it for the Wednesday.
I want to talk to you about something that is close to what you are doing.
Okay. So I think I have a lot of noise right now. So how about, I think it's better to write you an email a few hours later, not right now. How about that?
Okay. So according to the rules of our game, I'll follow in our discussions, I follow your advices. So you may. So please ask me. Your obligation to ask and mine to answer. Okay?
Okay.
But it happens only on Friday.
So I have like 2 or 3 topics in mind right now. So I give you a list by email.
Okay. So please
then you may choose one of them.
Just write me a letter, okay?
Okay. Thank you.
Okay, good. So see you next Wednesday.